General relativity. Imagine standing on a vast, flat plain. The ground stretches in all directions, and the sun rises high, providing light and warmth evenly. Now, picture someone setting a heavy object, like a massive boulder, in the middle of this plain. As the boulder settles, the surface begins to curve around it. The once flat ground bends and forms a dip, almost like a trampoline beneath it. This curvature of the ground is like the curvature of space and time described by Einstein's theory of general relativity, which redefined our understanding of gravity, space, and time. Before Einstein, gravity was understood through Sir Isaac Newton's theory. Newton saw gravity as a force that acted instantly at a distance, like a magnetic pull. If you dropped an apple, gravity would pull it toward the Earth instantly. This model worked well for everyday objects moving slowly compared to the speed of light. But when scientists observed stars, planets, and galaxies moving at near light speeds, Newton's model didn't work anymore. That's when Einstein changed everything with his theory of general relativity. Einstein proposed that gravity isn't a force but a distortion in space and time itself. Mass and energy bend and curve space-time around them, and this curvature dictates how objects move within it. Imagine space-time as a flexible, stretchy fabric. Mass and energy bend this fabric, and objects like planets and light follow the curves of space-time. To visualize this, think of a trampoline. If you stretch a large, heavy trampoline and place a ball in the center, the fabric will bend around it. If you roll a marble across the trampoline, it will follow the curve, moving toward the ball. Similarly, massive objects like the sun curve space-time, causing planets and light to follow curved paths. One famous prediction of general relativity is that massive objects like the sun can bend light that passes by them. This is called gravitational lensing. Imagine starlight traveling toward Earth. As it passes the sun, space-time curves, causing the light to bend. This effect has been observed many times, confirming Einstein's theory. The most dramatic consequence of general relativity is that gravity can bend space-time so much that it can bend light, alter time, and warp space itself. One of the most famous examples is black holes. A black hole forms when a star collapses, creating a gravitational field so strong that not even light can escape. According to general relativity, when a massive star runs out of fuel, it collapses into a point where space-time curves infinitely, creating a singularity. At this point, gravity becomes infinitely strong. Anything that crosses the event horizon, the point of no return, can't escape, not even light. The intense gravity bends light around the black hole, creating a visible boundary called the event horizon. Einstein predicted black holes long before they were observed. It wasn't until 2019 that scientists captured the first image of a black hole at the center of the galaxy M87. The image showed a dark circular shadow surrounded by glowing light, with a clear ring around the edge. This was the event horizon, and the light surrounding it was bent by the black hole's gravity, matching Einstein's predictions perfectly. Another important concept in general relativity is the interconnectedness of space and time. Space-time is not just the fabric of space, it's also how we understand time. For example, if you were traveling close to the speed of light in a spacecraft, time would pass differently for you compared to someone on Earth. According to general relativity, the faster you move, the slower time runs for you. This has been shown in experiments with fast-moving particles or highly accurate atomic clocks flown on jets. Time is relative, just as space is, and it stretches or contracts depending on your speed and the strength of gravity. This idea of time dilation has practical implications. If you were in a satellite orbiting Earth, time would move slightly faster for you compared to someone standing on Earth's surface. Without accounting for this difference, GPS systems would become less accurate over time. General relativity also predicts and explains gravitational waves. These are ripples in space-time caused by massive events like colliding black holes or neutron stars. The first detection of gravitational waves came in 2015, and since then, they've been used to study extreme cosmic events. General relativity changed our understanding of gravity, space, and time. It showed that these concepts are not fixed or separate, but interconnected and dynamic features of space-time itself. Space-time can bend, stretch, twist, and ripple depending on the presence of mass and energy. This flexibility leads to a new way of thinking about the universe, from black holes to cosmic expansion, time dilation, and gravitational waves. General relativity not only describes gravity, but reshapes how we understand the universe at its deepest level, opening a world of discovery and challenges that continue to expand human knowledge.